Here are some solutions for problems from Chapter 11, numbers 4 through 12, even. Number 4. The question is, a uniform solid sphere rolls down an incline. What must be the angle of the ramp if the linear acceleration of the center of the sphere is to have a magnitude of 0.10 g? Just for fun, I'm going to go through the derivation of the formula here. So this would be the gravitational force, mg. We know that there's also a normal force. That's canceled out by the cosine component here, gravitational force. This would be mg sine theta down the ramp. There's also a frictional force up the ramp. So the sum of all forces on the sphere is mg sine theta minus the frictional force. And the sum of all torques on the ball sphere is, the only thing that's causing a torque is the frictional force. Talked about that in class. So filling these out, that means that ma is equal to mg sine theta minus f. And here I alpha is equal to f times r. I for a solid sphere is 2/5 mr squared, and alpha is a over r. So one of those r's cancels out like that, and the other r cancels out like that. So that force of friction is equal to 2/5. Oops, sorry, that's a funny looking 5. 2/5 ma. Right. So back to here. Gives me ma is equal to mg sine theta minus 2/5 ma. And if I add that to the other side, first of all, I guess I can cancel out those m's. So if I add the 2/5 a over here, that gives me 7/5 a is equal to g sine theta. So the acceleration is equal to 5/7 times g sine theta. And the ramp here, I guess I know what this is. So this, in this case, they're saying that, what does the angle have to be? So that's 0.10 g, equal to 5/7 times g sine theta. The g's cancel out, multiply over here, that's 1/10. So that would be 7 over 50, right? When I multiply that fraction over there, upside down like sine theta. So that means that my angle is the sine inverse of 7 over 50, which is about 8.05 degrees. And that's the answer for part A. If you just dropped the formula that we have from class, you could do that. I think that would be okay. It's just a homework problem, but it's good to see where that comes from, right? And then the answer for part B, a block sliding down the ramp without frictionless, that doesn't make sense, without friction would be just g sine theta, right? And you can see that our acceleration here was 5/7 g sine theta. So it's always going to be less than. Why is that the case? Because some of the energy is taken up by the rotation of the object. So this is true not just for a solid sphere, but any object. The frictionless block is always going to have a greater acceleration because no energy is required for rotation. So that means it will be greater. Number 6. Got a graph here that gives the speed versus time for a 5 kilogram object of radius 6 centimeters that rolls smoothly down a 30-degree ramp. Scale of the axis is set blah blah blah, and they want to know what's the rotational inertia of the object. So what I have here, I know that its initial velocity is 0 and its final velocity at 1 second, so maybe I'll call that v1, so I can have that time there, is equal to, looking at the scale, let's see, their scale, the top is 4.0, but it's not at the top. It's, let's see, 1, 2, 3, 4, 5, 6, 7, 8. They divided it up into 8. So 4 divided by 8, that means each one of those is a half, so it's 3.5. Just reading that graph there. Right? It'd be an easy mistake to accidentally put the 4 there, I think, but it's not quite there. All right, so I think probably there's a couple ways to do this. I'll use our acceleration formula. I know that, let me find the acceleration first. So the time is 1 here. So that means the acceleration, using acceleration, is equal to final velocity times time plus initial velocity, but that's 0. So the acceleration is, my goodness, what have I done there? I got those the wrong way around. Sorry, I'm a little bit tired. In this case, we would have got away with it because the t is just 1, but that's the correct formula, of course. So the acceleration divided by 1 is just 3.5 meters per second squared. And then we went through the derivation here, so this time I'm just going to go ahead and say I know this, that the acceleration of an object rolling down a ramp without slipping is that, right? And I think I want to solve for the I here. So I'm going to go ahead and do some algebra here and solve this equation for I before I plug things in. So that would give me 1 plus I over mr squared is equal to g sine theta over a, subtract 1, and then multiply by mr squared. So that's going to give me I is equal to g sine theta over a minus 1, that whole thing divided by, let's see, I'm working there, or not divided by, rather, I'm going to multiply that to the other side at that point, so forget that, mr squared. So I think I go ahead and plug in my numbers now. So I would be equal to g times the sine of 30 degrees over the acceleration, which we found to be 3.5 minus 1, times mr squared, which, let's see, what did we have? It's got a mass of 0.5 kilogram and a radius of 6 centimeters, 0.06 squared. Now let's go ahead and jam that in to the calculator. So 9.8 times the sine of 30 is 1/2 over 3.5 minus 1 times 0.5 times 0.06 squared. And that gives me, oh dear, 7.2 rather, times 10 to the negative 4 kilogram meters squared. Cool. Number 8. What do we have? We have a potential energy graph that looks kind of like, I'm not going to do the whole scale, but it looks kind of like this. This is potential energy versus displacement. So I know some things about graphs like this. I know that the slope of a graph like this is the negative force, so that may come in handy. And I also know just energy considerations, that if I have some total amount of energy, then I can never exceed that amount. So let's see. So this graph shows potential energy of a solid ball that can roll along an x-axis. The scale on the u-axis is set by, this is 100 up here, and so this is 60. And the ball is uniform, so that means it is a solid sphere, right? It rolls smoothly, no slipping. It has a mass of 0.4 kilograms. And it's released at 7 meters, which is down here at the bottom, headed in the negative direction. It's going that way, with a mechanical energy of 75 joules. So before we look at the question here, let's think about what we know. It's down here at the bottom of the potential energy curve in a little valley here where it has 0 potential energy, which means that the mechanical energy at this point is all kinetic. But since it's a rolling object, that means it's kinetic energy of both types, translational plus rotational. So at that bottom point, if the total mechanical energy, since the potential energy is 0 at the bottom here, that means all of the 75 joules is split between those kinetic energies. If the ball can reach 0 meters, what is its speed there? And if it cannot, what is its turning point? So to get all the way back to 0 meters, one would have to have at least 100 joules of total energy to get there, and it does not. So it cannot reach 0 meters. So what's the turning point? Well, the turning point is wherever it's equal to 75 here. So I guess you could try to figure that from the graph, but it would probably be better to just write an equation for this line here and see where it intersects. So I'm just going to do a little quick algebra problem. This is the point 1, 100, and this is the point 5, 0. Right, so the slope of that line, it goes down 100 in 4 units. So the slope is negative 25. And the intercept, I'm just going to write it in y equals mx plus b form for now. So it goes through the point 5, 0, 5, 0. So the intercept would be 125, which makes sense if you imagine extending it back here, that it would hit about there. So the equation for my little line here, for this piece of this piecewise function, is that, and I want to know when it would be equal to 75. So subtracting that over there, so it looks like it's right at 2. So the turning point is at x equals 2 meters. Again, that's because that's where that point on the line, that's where it would have 75 joules. If that's how much total energy it has, it cannot exceed that, right? It's always going to have that much energy. So at this point, all of the energy would be potential energy, like it had rolled up a ramp, right? And then it would turn around there. Roll back down. Now, suppose instead it's headed in the positive direction of the x-axis when it's released at 7 meters with the same 75 joules. If the ball can reach 13 meters, which is up here on the flat, which it can, right? Because 60 joules there, then what's its speed there? And if it can't, what's its turning point? Well, it can reach 13 meters. And at that point, the total mechanical energy, which is equal to the potential energy stored in the sphere or in this system, right? Whatever it's from, they called it US, so I will too. Kinetic energy of rotation plus kinetic energy translation. And I know the total energy is 75 joules, right? Because it had 75 kinetic here and nothing else. And if it makes it to there, or rather when it makes it to there, it'll have 60 joules of potential. So you might have figured this 15 out without writing this equation down, but it all boils down to that. But there's 15 joules available for it to roll along. So how fast is it going? Well, rotational would be 1/2 I omega squared plus translational 1/2 mv squared is equal to 15 joules. They told us that this is a uniform solid sphere, so that means we can use 1/2 2/5 mr squared. Omega is v over r, so that's v squared over r squared plus 1/2 mv squared equals 15. Those r squareds cancel out, 2's cancel out, so I get 1/5 mv squared plus 1/2 mv squared. 1/5 is 2/10, and 5/10 is 7/10 mv squared is equal to 15. And I do believe they gave us the mass. Yep. So solving for v is going to be equal to the square root of 15 times 10 over 7. The mass will end up on the bottom here, which is 0.4. So solving for the velocity, the square root of 15 times 10 divided by, make sure all this stuff ends up on the bottom, 7 times 0.4. That's 7.3 meters per second. Cool. That's a good review of potential energy curves, too. Number 10. We have here a hollow sphere, radius 0.5. So it's a hollow sphere. That means we've got a 2/3 mr squared moment of inertia. It has a radius of 0.15 meters. Its rotational inertia is 0.040 kilogram meters squared. About a line through its center of mass rolls without slipping up a surface inclined at 30 degrees to the horizontal. At a certain initial position, the sphere's total kinetic energy is 20 joules. How much of this initial kinetic energy is rotational? Well, we have the total kinetic energy is 20 joules, and that's the sum of its 1/2 mv squared and its 1/2 I omega squared. Right. So, similar to the last problem, that's 1/2 mv squared plus 1/2 I omega squared, sorry, that's I is mr squared, times omega, which is v squared r squared. Omega squared is v squared over r squared, so the r squareds cancel out. And I think I don't need to finish this calculation to find the answer to this part, because this is just about the how much, right? Or maybe I do. So there's a couple ways to look at this, I suppose, right? I think my inclination is to think about this in terms of proportions. So the total here, the total amount of kinetic energy is a 1/2 plus a 1/3 mv squared. 1/2 plus 1/3 is 3/6 plus 2/6, or 5/6 total. And the amount of it that's rotational is 1/3. So 2/5 of it is rotational, and 2/5 of 20 is 8. So 8 joules of rotational energy. That's part A. I guess all of this was kind of part A, right? In part B, what do they want to know here? What's the speed of the center of mass of the sphere at the initial position? So here, what did they tell us? The radius? So I think here we have to actually find out what the m is. So they told us the rotational inertia, 0.04, is equal to 2/3 m times r squared. So I'm going to solve that for m. So let's do that. So 0.04 divided by 2/3 is the same as times 3/2, and divided by 0.15 squared. So the mass, it looks like, is 2.67 kilograms. And we're trying to find the speed. So I could go back to this equation here to find that. So I know that the total kinetic energy is 20 plus, and then I added these. This is 5/6 m we just found, 2.67 times v squared. And I can solve that for v. So moving that to the other side, I have 20 times 6/5 divided by 2.67, and I forgot to square root that, so I will now. And that's just about 3, it looks like. So the velocity is 3 meters per second. Part C. The part C, isn't there? When the sphere is moved 1 meter up the incline from its initial position, what are its total kinetic energy and the speed of its center of mass? So now it's gone 1 meter up the incline. You could do this a couple of different ways. You could use energy, or you could use kinematics. You could find the acceleration and then figure, after displacement of 1 meter, what would the velocity be then? Or you could use energy and say, since the ramp's at 30 degrees, after it's gone 1 meter up the ramp, it will have gone up a delta H of 0.5 meter. And you could do it that way. I don't know which way to do it for you here. Maybe, how long are we at now? 24 minutes? Maybe we'll do it real quick both ways. So if you wanted to do kinematics, you could say, well, I know that the acceleration of an object rolling on a ramp is, and this is true, it doesn't matter if it's rolling up or down the ramp, the acceleration is always down the ramp. So if the object's rolling up the ramp, the acceleration is still down, it just means it's slowing down, right? 1 plus I over mr squared. So I need to keep that in mind, that if this is my velocity, this acceleration, if I take that to be positive, this will be negative, right? This is up the ramp, and this is down the ramp. They have to be different signs, whatever you decide. So I think I have all this stuff. So acceleration is g times the sine of 30, which is 1/2, of course, for 1 plus the rotational inertia is 0.040 over mr squared. And you know what? This is we could use the trick here. The rotational inertia is 2/3 mr squared, and we're dividing by mr squared, so never mind all that. This is just going to be 2/3, right? You can put all the numbers in, and it's still going to be 2/3. All right, so that means the acceleration is 9.8 times the sine of 30 divided by 5/3, which is 2.94. And remember, since I'm calling this positive, I'm going to call this negative. 94 meters per second. And then I have a little kinematics problem. If that's my acceleration, my initial velocity is 3 up the ramp. It's going a displacement of 1 meter up the ramp, right? Everything here is in the direction of the ramp, so it really is going 1 meter, right? That's how far it's traveling in that direction. And I would like to know its final velocity. So Vf squared is equal to Vi squared plus 2a delta x. We would certainly expect to find a number that's smaller than 3, right? If we don't, we know we did something wrong. So to find the Vf, I'm going to have the square root of Vi squared plus 2 times the acceleration, which is negative 2.94, times 1. So about 1.77, looks like. So that's one way to do C. The other way to do C, I'm kind of running out of room here, so sorry about that. I'm going to have to switch to a new sheet. So here's the alternate solution for C using energy. If you know that the energy before, if we take its starting point to be the 0 height, it's a combination of kinetic and rotational energy. And then when it's rolled some distance up, then it now has gravitational potential energy, 1 meter's worth, or 1 meter times the sine of 30, rather, right? It's raised up half a meter because the ramp's at 30 degrees, and if it goes up 1 meter this way, then it's gone half a meter further away from the center of the Earth, right? And that would be plus. It's still moving, so it still has its new translational and rotational kinetic energies. These are the initial ones. And they told us here that this initial is 20, right? So 20 is equal to, the change in gravitational energy is m, which is, what was the mass? It was 2.67 times g times the change in height is 0.5. And that's plus that combination of those things. So I'll just subtract that over to the other side. I got 20 minus 2.67 times 9.8 times 0.5. So 6.9 about. And then the sum of those two. But remember from the work that we did earlier that the sum of those two things, this is 1/2 mv squared and this is 1/3 mv squared, and when we add those together we get 5/6 mv squared. So the V is equal to 6/5 times 6.9 divided by the mass. And hopefully that'll give us the same answer. So 6/5 times 6.9 divided by 2.67 is, oh, and we need the square root of that. Just kidding. Here we go. So what do we get? 1.76. So just but for rounding, we got it slightly different, off by 100th. So two ways to do that. kinematics or energy. And remember, we can use kinematics because there is constant acceleration. And let's see, we still need to do part, or was that part D? Did I do the parts in the right order? Maybe I didn't. Oh, they wanted its total kinetic energy. So the speed of its center of mass, I just did, both of those were actually answers to part D, weren't they? And they want the total kinetic energy I found along the way here. So you got that. So I guess since they asked that in part C, it might be more compelling to do it this way. Although if you did part D first and you got the answer, then you could just plug that into this to get that number, because you know that's the total kinetic energy. If you're looking at that and thinking, why is the total kinetic energy 5/6 mv squared? I thought it was 1/2 mv squared. Remember that this is what we got when we combined these two, right? The 1/2 mv squared plus the that cleaned up form of the 1/2 I omega squared. Right, last one, number 12. Let's see, solid brass ball. So we assume that it's got a 2/5 mr squared moment of inertia. Solid brass ball of mass 0.280 grams. That's very small, like a little BB. Will roll smoothly along the loop track when released from rest along the straight section. The circular loop has a radius of 14 centimeters, and the ball has a radius. That double inequality sign, that just means the r is much less than r, which means we can ignore the radius of the ball for calculations of potential energy and stuff like that. It's much smaller. What is h if the ball is on the verge of leaving the track when it reaches the top of the loop? If the ball is released at height h, 6r, then what's the magnitude and direction of the horizontal force acting on the ball at point Q? All right, so what we know about this kind of situation, the borderline situation where it's just going to barely make it through the track, that's the situation. We know that if something's moving in a circular path, like at the top of the circle here, there must be unbalanced force toward the center of the circle, and that unbalanced force must equal mv squared over r, right? In the borderline condition, we know that the normal force, if it's just barely going to make it, that's where the normal force backs away to 0. And the only thing acting, pulling the thing toward the center of the circle, is gravity. The normal force has backed off to 0. We've seen this problem before, right? So that means the only force is gravity. So the speed that it would have to have, any object, whether it's rolling or not, would be v is equal to the square root of gr. That's how fast it has to be going. And that's how fast it has to be going when it gets to the top of the loop. So if we want to figure out what height it has to be released at, this now becomes an energy problem. Roll down the ramp, around the loop, up to here. So that's r. Of course, that's also r. And this is a distance h. So the change in its potential energy from here to here is the change in height. So it's h minus 2r. They call it capital R, they did. Right? That's how much the change in potential energy. So that's how much kinetic energy it's going to gain. Now this is different from the problems of this type that we did before, because now the kinetic energy, so at the top here, we have all that, and here we have this, right? We're taking this to be the 0 height. It's going to drop by h minus 2r. So the difference is now that the energy transfer, it's going from this to both of these. It has to share here. So let's flesh out that equation. Gravitational potential energy is equal to translational potential energy plus rotational. This is mg delta H, which is H minus 2R. That's equal to translational 1/2 mv squared plus rotational 1/2 I omega squared. Okay? Let's see, before I start plugging numbers in, let me just try to clean this up some. Mg times H minus 2R is equal to 1/2 mv squared. I know a lot of these things now, right? Plus 1/2, and this is a solid ball, right? So they told us that. That means we know it's 2/5 mr squared, and then omega is v squared. Omega squared, rather, is v squared over r squared. Right? So our r squareds cancel out. The 2's cancel out here. The masses cancel out. A revoir. And we've seen this before, but I went through it again. This is 1/2 plus 1/5 mv squared, which is 7/10. The m's have canceled out, so just 7/10 of v squared. That's g times h minus 2r on this side. And we're trying to solve for h, right? What's the height that we'd release it from? So, the height we would release it from here is going to be h. I'm going to do a little bit of algebra here. 7/10 v squared over g, dividing by that, and then I'd have to add 2r to that. I think I'm ready to calculate that now. So let's see, I've got 7/10 times the velocity. Oh, and I should have, you know what? I forgot to make that substitution because I can do that. So v squared would be equal to gr, and then the g's would cancel out. So actually I have 7/10 r plus 2r, right? So 2.7 r. And what's the r? 14 centimeters. So that's about 38 centimeters. Right, that's a pretty involved problem, I think. And again, you know, I think our book does a good job of reminding us of things like that. It's definitely good to think about that situation again. That was part A of that problem. Part B, what are the magnitude and direction of the horizontal force acting on the ball if we release it from 6r? So I think we've set ourselves up well. So this is just B and C. The direction, of course, will just be toward the center of the circle, right? When it gets to point Q, the horizontal force, it's direction toward the center. So same thing. I'm going to release it from up high, and then I'll take the ending point at point Q now. Let me redraw this here. At point Q. So I'm releasing it now from 6r, and then it's going to end up here. If it's at point Q, that's an r, 1r above here. So the delta H, the change in height, is 5. Note that, please. So I got mg delta H is equal to 1/2 mv squared plus 1/2 I omega squared. But come on, I mean, we know now that this is 7/10 mv squared, right? We've done that already in this problem, so you'll give me that, right? So that means I have mg delta H is 5r. It's going from 6r down to r, is equal to 1/2, this adds up to 7/10 mv squared. So the m's cancel out, and I get that the velocity here is equal to 10/7 times 5GR, and I'll have to take the square root of that whole thing there. All right, so square root of 10/7 times 5 times 9.8 times the radius, which is 14 centimeters. So it looks like it'll be going 3.13 meters per second, or thereabouts. Oh, but that's not what we wanted to find. Sorry, that is how fast I think, although they don't have that answer there. They wanted to know how much force is there on it. Well, we know that the force, the centripetal force, which would have to come from the track, it would have to be that horizontal force, is equal to mv squared over r. So I guess since I found that, I'll just use that number, right? You could use this form of it, which would be interesting, maybe. So I'm going to just do m, what was the mass? It was really small, wasn't it? 0.00028 kilograms times the velocity squared over r. So 0.00028 times 3.13 squared divided by 0.14 is equal to that. So that's about 2.0 times 10 to the negative 2 newtons. How's that sound? And I guess for reasons of rounding, well, you don't have the even answers anyway. I ended up a little bit off from the book, but that's because of my rounding. Probably that number there. So you could have, let's see if we can get the exact answer the book has. You could have taken this and said, well, I know this is true. So in this expression here, the centripetal force would become m, and then v squared is this whole thing without the square root sign, times 10/7 times 5gr over r. So the r's cancel. So if I just do this straight calculation here, let's see if I get what the book has. So that's m.00028 times 10/7 times 5g. Yep, and that gets me what they have. So it's just for rounding this number that I got something slightly different. So there you go. Good stuff. Rollin', rollin', rollin'.